Earth is not the only world adorned with a radiant atmospheric phenomenon, the aurora borealis. In fact, in the solar system's auroral competition, Jupiter will be the clear winner. The so-called king of the planets is crowned with the most powerful auroras in the solar system, constantly rotating above both its poles. Since they only glow with invisible wavelengths, we cannot see them with the naked eye, which is why they were only discovered 40 years ago. Since then, scientists have wondered how these auroras cause periodic bursts of X-rays. Now they think they have solved it. Using simultaneous observations from the Jupiter-Juno probe and the XMM Newton Space X-ray Observatory, a team of scientists led by planetary scientist Zhonghua Yao of the Chinese Academy of Sciences in China has linked the X-ray bursts to fluctuations in the magnetic field lines of the gas giant. These oscillations generate waves in the plasma that propagate along the lines of force of the magnetic field, periodically causing heavy ions to collide with Jupiter's atmosphere, releasing energy in the form of X-rays. We've seen Jupiter generate X-rays for 4 decades, but we didn't know how it happened. We only knew that they were formed when ions hit the planet's atmosphere, explained astrophysicist William Dunn at University College London in the UK. We now know that these ions are carried by plasma waves, an explanation that has not been proposed previously, although a similar process causes the Earth's own aurora. Hence, it can be a universal phenomenon present in many different environments in space. Here on Earth, auroras are created by particles emitted from the Sun, collide with the Earth's magnetic field, which sends charged particles like protons and electrons whizzing along the magnetic field lines to the poles, where they rain down on Earth's upper atmosphere and collide with atmospheric molecules. As a result of the ionization of these molecules, amazing dancing lights are born. There are several differences on Jupiter. As noted earlier, the auroras are constant and constant. This is because the particles are not solar, but from Jupiter's moon Io, the most volcanic world in the solar system. It constantly spews sulfur dioxide, which is immediately removed due to the complex gravitational interaction with the planet, ionizes and forms a plasma torus around Jupiter. And then there are X-ray pulses. To figure out how they are generated, the research team studied the planet using simultaneous observations of Juno and XMM Newton made on July 16 to 17, 2017, for a total of 26 hours. During this time, Jupiter was emitting X-rays approximately every 27 minutes. Based on these observations, the team linked the Juno plasma observations with the XMM Newton observations of X-ray auroral bursts. Using computer simulations, they determined how these two phenomena can be related. The team concluded that the collapse of Jupiter's magnetic field creates waves of oxygen and sulfur ions that spiral along the magnetic field lines to the poles of Jupiter, where they rain down, collide with the atmosphere, and generate flashes of X-ray light. These waves are called electromagnetic ionic cyclotron, or EMIC, waves, and they are also associated with the twinkling auroras here on Earth. It is currently unclear what is causing the collapse of Jupiter's magnetic field. This could be the influence of the solar wind, the circulation of heavy materials in the Jupiter magnetosphere, or surface waves at the magnetopause, the outer boundary between the magnetosphere and the surrounding plasma. Be that as it may, compression is occurring, but the fact that the same mechanism EMIC waves has been associated with auroral emissions in two such very different worlds suggests that this may be quite common in the solar system, and also in the galaxy beyond. Now that we have identified this fundamental process, there are many opportunities to explore it further, Yao said. Similar processes are likely to occur around Saturn, Uranus, Neptune and possibly exoplanets, with different types of charged particles plowing the waves. The results show that electromagnetic waves may play an important, previously unnoticed role in the ion dynamics of Jupiter's atmosphere, and may help us better understand plasma processes in the galaxy.